interrupt and they will raise hands, and then I will tell you.
Yeah, that's great.
All right.
Okay, we are ready.
Okay. Yeah, maybe just a second. Let me put in order the slides just to make sure that you know, I can share them, because that would be nice. Just a second, sorry. Okay. Okay, I think now I can even see my slides. Okay, great. Then everything is ready. Sorry for the delay.
Would you like to go in play mode, in presentation mode, or?
Sure, I can. Here it is. Mm-hmm.
Thank you.
All right, then we are ready to start. It's a pleasure for me to introduce the last lecturer of the day, which is going to start with the first lectures on the standard model. This is Stefania Gori from University of California, Santa Cruz. She has been working in several topics of high energy physics. She's an expert of Higgs physics, flavor physics, beyond the standard model, and she will talk, give an introduction, and go more in details about topics of standard model, flavor, and all that. Please.
Okay, thanks a lot for the introduction. Thanks for inviting me to this nice summer school. Here I have so first, welcome everybody, and here I have the first slide where I introduce a little bit myself. Well, that's my name, and this is the university where I am. University of California, Santa Cruz. And yeah, I pasted here a couple of pictures of our beautiful campus in the middle of the redwood forest, so a little bit of advertisement. And then here you can find my contact, so the email address, and everyone is invited to send me an email with you know, questions, or if you want to have some more references, just welcome to contact me. So as Giovanni was mentioning, this course is going to be about the standard model of particle physics. And here in this first reference, what I've done is to collect a couple of references that could be useful for our study of the standard model. As we see, the standard model is obviously very much based on quantum field theory, and here I report three beautiful books about quantum field theory, and by Schwartz, Peskin, and Schroeder, and Maggiore. Some books about the standard model, as you can see here, and then also some review paper about the standard model. So these are general references, and then throughout the course, I will show you more specific references on specific topics. Okay, but this is so these references are here for completeness, and I would invite you to take a look. But obviously, you know, they are most of them are books, so they contain a lot of information, much more, of course, than what we will discuss during this this course. Okay, so this is just to start, and now let me switch to my iPad. So I will stop sharing the slides, and let's see. Here is my iPad. Okay. So let's start with the goals of these lectures. So what? Let's see. Goals. Also, please interrupt me if you don't read in my handwriting, in case there is something not clear. That's great to know. So what are the goals? So we want to learn these three different things. So the first thing we would like to learn is how to build the standard model Lagrangian. So how to build the standard model. I will always abbreviate with SM, so the standard model Lagrangian. So this is, as we'll see, we have some what I would call rules. So we have to follow the rules of quantum field theory. We have to apply gauge invariance. We have symmetries to use. And then we have a set of ingredients that are our particles, the particles that we have discovered. So this is obviously quite theoretical, and this, as I said, is basically learning QFT for the standard model. But then also we would like to understand how to test the standard model Lagrangian. So we will link what we have learned about the standard model Lagrangian to experiments. And we see indeed that things work, right? That we have quite a lot of tests, quite a lot of measurements that are confirming this framework of the standard model that we'll study this week. But then the last topic that will leave quite a bit of room for going beyond the standard model and being creative beyond the Lagrangian of the standard model. We'll discuss and we want to understand what are the anomalies in data. So we see that there are some measurements that don't fully agree with the standard model prediction, and then we want to understand a little bit what can be wrong, and if especially if these anomalies are staying. And the focus here will be on something that is pretty recent, that is a new measurement of G-2 of the muon. That is probably quite a few of you have heard about it, and this is quite an exciting new measurement, so we would like to understand it a little bit. And then I will introduce why we want to go, or we would like to go beyond the standard model. So what are the questions that we would like to address, and why particle physicists study also beyond the standard model physics? Okay, so these are the goals, and this is what we would like to learn this week. So I've seen maybe there is a question in the chat. Let's see.
No, don't worry. I will
okay. Okay, great. Thank you. And so this is for the goals, and then for the topics that we will discuss. So for today, what we will do is mainly to introduce tools. So we'll talk a little bit about Lorentz invariance. I will recall some notions about QFT, speak about natural units, and a little bit about symmetries. This topic about symmetries, we'll see how much we do today, or we'll finish them tomorrow. And these are the tools that then we'll use to start building the several pieces of the standard model Lagrangian. So for tomorrow, for Tuesday, our focus will be on quantum electrodynamics and the weak interactions. Then Wednesday, we'll talk about electroweak symmetry breaking. And the Higgs. So we'll take, what we had learned on Tuesday, and we see how to break the symmetries that are, associated to the weak interactions. On Thursday, our class on Thursday will be dedicated to flavor physics. So the flavor sector of the standard model. And then finally on Friday, we'll do a little bit of introduction to neutrino physics. And we'll link neutrino physics to what we learned about flavor physics the day before. We'll speak about, as I mentioned already, experimental anomalies. And why beyond the standard model physics. Okay, so that's the plan for these lectures. Okay, yeah. So if there are no questions about the overall organization and the goals, we are ready to go into the details. Okay. Okay, and then please just ask questions and interrupt me as much as you can. That's more fun. Okay. So let's start with our first chapter. So this will be some overview plus tools. So this is the chapter of today. So the first thing I want to discuss with you are the fundamental principles of the standard model. Okay, so first of all, let's start let's go back in time. Let's think a little bit again about Newtonian physics. So in wrong color. In Newtonian physics, say that we want to describe the system of many particles. And what we can do is to introduce the set of generalized coordinates. So introduce a set of generalized coordinates. Let me call them xi and the time derivative of xi. So this will be the derivative with respect to time. And then if we want to describe the system, what we would like to understand is what is the time evolution of these coordinates. And to do that, what we do is to minimize the action S that is defined as the integral of the Lagrangian of the system that does depend on these generalized coordinates with respect to time. So if you want to study the time evolution between t1 and t2, you need to solve this integral here. And once you minimize, you will find some paths. So basically what you will need is to solve the Euler-Lagrangian equation of motion. So solve the Euler Lagrangian equation of motion that tell us that there is a relation between the derivative of the Lagrangian with respect to x dot and the derivative of the Lagrangian with respect to x. Namely, what we know is that if you take the time derivative of this object, this is equal to this. So what we see from here is that once we know the Lagrangian, L, we can find the path of the several particles x of t. And this, of course, is up to initial conditions. So in the case of above, what we'll need to define are the initial conditions at t equal to t1. Okay. Now this is what we know from Newtonian physics, and then we can generalize this to field theories. So what happened to field theories? So in field theories, the message is the same, namely that we need to know the Lagrangian in such a way to understand the evolution of the several fields. And in field theories, what we do is to define the action again as an integral of the Lagrangian that now does depends on the fields. So we call this field phi and the derivative of the fields. And this time we do the integral in 4 dimensions, so d for x. And then the Euler Lagrangian equation of motion can be written as, will be written as in this way, again, relating the derivative of the Lagrangian with respect to the derivative of the field. And this will be equal to the derivative of the Lagrangian with respect to the field. Notice that I'm using here relativistic notation. That will introduce briefly. But here, before entering into those type of details, what I want to really to highlight here is that the conclusion. So the conclusion is that we need to know the Lagrangian. And then hopefully we can solve this differential equation in such a way to find the evolution of the several fields. Okay. I say hopefully because obviously depending on the nature of the Lagrangian, this differential equation here can be quite complicated. And actually comment for the expert is that we might want to use perturbation theory if this this differential equation is too complicated to solve otherwise. Okay, but then following this message, this is our motivation to try to learn how to write down the standard model Lagrangian, okay? And then we can understand the phenomenology of the several particles of the standard model. So I see there is a question.
Yes, there is one question by Sonali Patnaik. Please.
Hello. Hi, Stefania.
Hello.
Is it audible?
Yes.
Yes.
Yeah, here I want to ask that what is the motivation of introducing action, like integral of Lagrangian? What is the physical interpretation?
So So in Newtonian physics, we know that the so what the action is so we introduce the action as in quantum mechanics as the quantum so let me back up a little bit. So if you think about the Planck constant, so the Planck constant is the quantum of action, and then basically you can define all your physics using this this quantity that is the action. That is basically. I mean, you see from these relations here that you can build, you can study your physics using the action or the Lagrangian or a Hamiltonian in a similar manner. Just that the way that usually we start is in an axiomatic way, saying that you build this action here, and what your physics does is to follow paths that are minimizing this action. So this is the axiomatic way of defining your physics that describe whatever system that you like, basically.
So the physics starts with the action.
Yeah, that's the way I would say it. In this, as I said, this is mainly an axiom, right? An axiom, sorry, not an axiom. Namely that your physics will, so your system will minimize the action. And then from there, you learn all your, all your dynamics.
Okay. And again, by minimizing, what do you mean?
So you have this quantity that is defined here, for Newtonian physics, but then we said that this is the same for field theory, and then you can so this quantity S will be a function of x and x dot, and then you minimize your function, right? You find the minima of this function as a function of x and x dot. And if you do so, you can demonstrate that you end up obtaining this Euler-Lagrangian equation of motion that is relating x and x dot.
Okay. Thank you. Yeah.
Sure. Any other question? Okay. Yeah, thanks for the question. Okay. So let's introduce a little bit the fundamental principles of the standard model Lagrangian. So what are the rules that we would need to follow in such a way to be able to write down the Lagrangian? Fundamental principles of the standard model. And so as we'll discuss quite a bit in details, but this is, for now, just an overview. So the Lagrangian, actually, not only of the standard model, but this is the focus of these lectures. So the Lagrangian is based on the following principles. So we'll have a set of symmetries that we'll discuss a bit today and the rest throughout the course. So we'll have symmetries. Then what we do is to apply unitarity. So we need to write down a Hamiltonian that is Hermitian. Then what we also impose is renormalizability. So the reason is that we want to have finite predictions for the physical observables that we want to measure. And therefore we need to have a Lagrangian that is renormalizable. So we need to have only a finite number of amplitudes that are diverging in the ultraviolet. And then finally, typically what we say is that the Lagrangian of the standard model is also based on minimality. Namely that we use only a minimal set of objects to write down our Lagrangian. This, if you want, so as you see, I put this word in quotation marks, and the reason being that the particle content of the standard model, as we'll see, is highly non-minimal. So the particle content of the standard model is non-minimal, since, as we'll discuss quite a bit, we have a set of gauge bosons, we have a lot of fermions, and one Higgs. But then you might wonder, okay, what we mean with minimality? We mean that we don't add particles that we have not at least observed, right? And but still, you know, there is in mind this idea of having a Lagrangian that describes a system that is as minimal as possible. Okay. And in fact, in this context, I can show you maybe a slide. So I will switch for a few minutes to my slides again. So let me stop this sharing here, and I will go back to my slides. I guess you see my slides, right? So this is, you know, the particle content of the standard model, and we'll study this quite a bit in details this week. These are the gauge bosons that I was mentioning. We have the gluon, the photon, and the weak gauge bosons, the W and the Z, one Higgs, and then all these fermions. We have quarks and leptons with different electric charge. Okay. And what is quite cute, and that's why I like to present this slide, is that the next slide, it took us quite a bit of time to discover all these particles, and there is this nice cartoon that actually I took from the Economist that shows when we discover all these particles, if you're curious. So this is a nice summary. Starting from the electron, we have here the experimental discovery by Thompson. And then we have here in 2012 the discovery of the Higgs boson at CERN. And also what is interesting of this cartoon, as you see, that is that each particle has two dates. So there is the first date, you see, here and here and here. They correspond to the time that the particle was first theoretized by someone. And then afterwards, you see the time of the experimental discovery. And sometimes you see that it takes quite a bit from you know, the theoretical idea to the experimental discovery, especially as we see here for the Higgs boson that took us, as we'll discuss quite a bit in detail, took us quite a bit of time. And on the opposite, there are also particles that are discovered sort of by chance as the muon, in the sense that we didn't expect them theoretically, and that's why, you know, there is the famous sentence by Rabi worded that we didn't expect the muon discovery. But I see that there is another question.
Yes, by Carl.
Yeah.
Please.
I have a question related to the unitarity of Lagrangian? Is it only related to the hermiticity of that Hamiltonian, or is there something else it is also related to?
Yeah, so you can think about unitarity in many different ways. So what I mean with unitarity is simply that Hamiltonian is emission, so that you have your time evolution operator that is unitary. Then you can, depending on the research that you do, you can think about perturbative unitarity and other type of unitarity issues. But here, what I mean in this context is simply that the Hamiltonian is emission. Yeah. Okay. So here we are back to my iPad. Okay, so this is what I wanted to say about minimality and the particle content of the standard model, and then for symmetries. So I see another question maybe before symmetries. Go ahead.
Hello, ma'am, am I audible?
Hi.
Yeah, so when it comes to question of minimality, does it also tie into the fact as to why we don't use higher order Lagrangians in our theories?
No, so what I mean here with minimality is that we use just the minimal set of objects, of particles, of fields that we need to describe nature. A higher order, I mean, this for perturbation theory, and this is a complete different thing. I mean, as we'll see a little bit about perturbation theory, this is a sort of a tool that you need in such a way to make predictions and to do calculation using your standard model Lagrangian, but this is different from minimality, the minimality that I'm mentioning here.
Okay.
Sure. Maybe one more question and then, yeah, go ahead.
Hello.
Hey.
I want to know, while constructing the Lagrangian under certain symmetry, why do we want the terms in the Lagrangian to be singlet under that particular symmetry?
Oh, why don't we discuss this when we discuss the gauge symmetries? But yeah, so this is absolutely. So at the end of the day, we'll introduce some gauge symmetry or some symmetry, and then especially, when we discuss gauge symmetries, we see that several terms of the Lagrangian need to be singlet under this gauge transformation. Yeah. Yeah, I would delay this question to when we discuss gauge symmetries. I think it's much better. But if it is still not clear, I would invite you to ask again. Okay.
Okay. Mm-hmm. Sure. Thank you.
Sure. Okay. So if there are no more questions, so here let me do a couple of brief comments about symmetries, and then this is something that we'll study quite a bit more later. So for symmetries. So the set of symmetries that we'll discuss this week. So we'll introduce a little bit the Lorentz symmetry, and we'll see how to use it to build standard model Lagrangian terms. Then, as I just mentioned, we'll discuss gauge symmetries. And we'll see that the standard model has a quite large gauge symmetry that is SU3 times SU2 times U1. We will see, and let me put this maybe in parentheses, that we do not impose global symmetries. But they are accidental. meaning that they come out for the standard model Lagrangian ones that we follow the other set of rules that I will give you during these classes. And in particular, we'll see that in terms of global symmetries, at least approximated symmetries, the standard model Lagrangian has quite a large set. We see that we have, as examples, we have a large SU3 to the 5th power flavor symmetry. We'll discuss this on Thursday when we'll discuss flavor physics. Then we see that we have a lepton and baryon numbers that are again global symmetries of the standard model. We'll discuss a tiny bit about those, not too much, and then we see that we have another symmetry that is what we call the custodial symmetry. Just to introduce a little bit the names, that is again an approximated global symmetry of the standard model. And we see indeed that how these symmetries are broken, even though they are indeed, as I said already, approximate symmetries of the standard model Lagrangian. Okay. So this is just a few comments about the symmetries that we'll need to understand a little bit in order to be able to build the standard model Lagrangian. And now for the last few minutes before the break, what I wanted to do is a few reminders about Lorenz transformations and relativistic notation. So let's introduce a little bit Lorenz. Connected to these Lorentz symmetries that I mentioned here. So the first reminder that I wanted to mention in this context is so how do we relate two observers that are moving with respect to each other with a velocity that is not too far away from the speed of light. So the classic example is that we have two observers. We call them O and O prime. And the system of coordinates of these observers is the following. So we have here the first one with some time t. This is O, the observer O. And then we have the second one. And then this second one is moving at a speed that I call v0 with respect to the first one. And then we have a Lorenz transformation that is relating the coordinates that of an object as seen by the first observer to the coordinates of the same object as seen by the second observer. So the Lorenz transformation in this case that I am moving on the x-axis is given by the following equation. So instead of the speed of light times time, x, y, z, what we have is, c t prime that is given by gamma ct minus beta x. This is minus beta ct plus x. And then this. So as you see, we don't have as we expect, we don't have any transformation for y and z. And here I define this beta as v0 over c. So v0, again, this was the speed that we see here. And then the gamma factor is equal to 1 minus v0 square over c square. Okay. This is our Lorenz transformation we can obviously generalize it if we have some motion in a generic direction that is not necessarily x. And what is interesting here, these Lorenz transformations, is that we can build invariants. So if we write down this delta square that is defined as c square t square minus x, y, and z. So this quantity is invariant under Lorenz transformations. So I can write down my delta prime square as c square t prime square. And this is simply, again, equal to delta square. This is what we mean with invariant, no matter what type of Lorenz transformation I do. Okay. And this delta has actually a name. So this is the proper space time distance. And actually, yeah, we can write it in a little bit more compact form as, let me write it here. So this delta square is equal to eta mu nu. Sorry. So this is a quantity that we use quite a bit. That's why I introduce it here. Times x mu x nu. Sorry. Well, this eta mu nu is our metric that is given by 1, minus 1, minus 1, minus 1, and all the rest is 0 of diagonal. Okay, and obviously this is not the only invariant that we can write down, and we see that the way that we can write down Lagrangian terms is to impose that we have Lorenz invariant objects. Another object that we'll use quite a bit that is also invariant is given by this combination here. So if you take, say, a particle with energy E and momentum given by px, py, and pz in the several directions, then we can build the following invariant as E square over c square minus px, py, and pz. And this is again an invariant. I might ask you what invariant is this? I don't know if someone can answer. Maybe if anybody knows, one can say it. So this is actually a physical quantity that is given by, what is this? Yeah, someone. Oh. So
it's the mass squared.
Yeah, very good. So this will be the mass square of the particle. And this doesn't depend on the Lorentz frame that we are considering. So we learned that indeed we have this invariant and this other invariant. And then the last thing that I wanted to mention concerning Lorentz is just a little bit of notation that will be useful for later, namely that we can relate the 4 vectors with the index up or down in the following manner using this eta mu nu, namely that x mu with the index down is equal to eta mu nu x nu, and this will be given by ct minus x minus y minus c. And then we can define the derivative with respect to this for vector, namely, so the derivative with an index mu that is given by derivative with respect to x mu. And then in terms of Lorenz transformation, we have the x mu that goes into x prime mu that is given by this matrix with two indexes, x nu. So this was, the matrix that we wrote down explicitly just above in the case of a transformation on the x direction. Here you see what I'm putting this red arrow. And a useful relation is that if you apply two of these Lorenz transforms, then you get again your metric. Okay. And you can check this relation for the Lorenz transform of above. So you can check that so the Lorenz transform of above in a matrix form can be written in the following manner. And then you can apply to the metric 1, minus 1, minus 1, minus 1. And then you have the same object here. All of these are zeros, and then you have a 1 here on the diagonal. And then indeed, you get the same metric. Okay, this is just an example if you take a Lorenz transform on the x-axis. Okay, and this relation will be actually useful for later. That's why we have to keep this in mind. Okay, so these are the little reminders that I wanted to mention for concerning Lorenz. And yeah, now we are ready to take a break. But of course, I'm happy to take questions in the meantime.
Okay, thank you. So we'll have a break for 5 minutes and we'll resume.
Okay.
Since there is one raised hand, maybe we can ask questions.
Yeah.
My ban, maybe you want to ask a question now?
Hello.
Hi.
Will you teach leptogenesis in your course?
Sorry, can you repeat? I didn't understand what you said.
Will you teach leptogenesis in your course?
No. Yeah, that's something that goes beyond what I'm planning to do. Yeah.
Okay, fine. No problem.
I can give you references if you're interested to this topic, but it is something that, yeah, we won't discuss. Yeah.
Okay, fine. Thank you.
Sure.
There's another one by Sonali.
Hey, hi. So I want to ask again that what difference it would make if we introduce Hamiltonian and not Lagrangian initially?
Yeah, so you can work both with Hamiltonian formalism or Lagrangian formalism. Yeah, that's so you can formulate your field theory both in terms of a Hamiltonian or Lagrangian. Typically, people, what they do is to use the Hamiltonian formalism, and then you can write down your time evolution using Hamiltonian, but you can also use simply Lagrangian formalism. Yeah.
Okay, so the dynamics would be same.
Say it again. Sorry, I didn't hear what you said.
The dynamics would be same.
Yes, yeah, that's right. That's right.
Okay.
Mhm.
Thank you.
Sure. Okay, I think, yeah, we can start again. Okay, excellent. So now let's see how to apply what we have learned on simple Lagrangians. Let's build simple Lagrangians. That will bring two examples. So one is for a real scalar field phi. And then the second one is for a fermion field. Fermion field, so a Dirac fermion field psi. Okay. So let's start with one. So what I can write down in my Lagrangian. So since this is a scalar field, let me try to write down these two terms and then we'll see if they work. So the first term that I can write down is the term of this type. So this, yeah, this is a term that we'll discuss a little bit, and then let me put maybe a factor of 2 in front, okay? And then the other thing that I want to write down in my Lagrangian is a function of the field, v of phi, and this will be my potential. And you see that, I'm not obviously putting any Lorentz index here. This is just, a scalar function of this real scalar phi. Okay. Now this field phi is the field that will describe a spin zero particle or quantized. And we see that actually the Lagrangian that we wrote down here is very similar to the Lagrangian that we can write down for the Higgs particle. Okay, but this, for later. Now, if we write down a Lagrangian like this, so first of all, we can check if it is Lorentz invariant or not. So the first question is it Lorentz invariant? Now, for the transformation of the field, since this is a scalar field, so this field will depend on the coordinate x. So here, to be precise, actually, so this will be, I have 4 components, so I have time x minus z. And actually, since this is a scalar field, what we know is that we have that the transformed field completed at x prime is equal to phi of x. Okay. So using this transformation, it's trivial to demonstrate that the potential V of phi is trivially invariant under Lorentz transformations. A little bit less trivial is the transformation of the first term that I wrote down here in the Lagrangian. So let's see what happens to it. So what we have learned is that x mu transforms as in the following way, and therefore, if we take the derivative of the field phi, this will transform as a Lorentz transformation. Then we have the derivative prime and phi prime. Well, with derivative prime, what I mean is simply the derivative with respect to x prime, the Lorentz transformed of x. And therefore, the first term of the Lagrangian, the mu phi, will transform in the following way. So I have a few indexes here that I have to take care of. Then I have my metric eta mu nu, and then I have the transformed derivatives of the transformed field prime and prime. Okay. So what I've done is simply to have 2 transformations each corresponding to one of these derivatives. And then you see that I have this combination here that we already saw above. So let me highlight it. So this object here is this thing here that we saw. So this tells us that indeed this is given by eta mu prime nu prime derivative of phi prime derivative of phi prime, and then this is equal. Let's do all the steps to mu prime prime phi prime, and this is indeed invariant. In the sense that this is equal to the Lagrangian term that we were starting with. So using these Lorentz transformations that we introduced 10 minutes ago, we can show that indeed this would be a term of the Lagrangian that is allowed by Lorentz. So we're happy that we can write it down. Okay. So that is just you know, a simple example to see how to use Lorenz transformations to see what we are allowed to write down in the Lagrangian and what we are not. Okay. I see some questions and some hands raised.
Yes, the first is by Engame.
Hi. I just wanted to ask, has there ever been an instance of the Lorentz invariance symmetry breaking? Like, has the Lorentz symmetry ever been broken, basically?
So there are tests, meaning experimental tests to see if the Lorentz symmetry is a, you know, a exact symmetry. And so there are bounds on the possibility of breaking Lorentz, but so far there is no evidence really for experimental evidence for breaking Lorentz symmetry. But yeah, there are experimental searches for that and yeah, measurements.
I see. Thank you.
Next is Maivan.
Ma'am, I have a question. You have said that for the Lagrangian, in order to check the Lagrangian is Lorentz invariant, the V of phi has to be trivially invariant. But it is seen that usually it is seen that when we make a model, we check for the minimization of the potential part under the symmetry that has been considered. So why is it done, and how is it different from this concept?
Sorry, can you repeat the question? I'm not sure I got this. Can you say that
Ma'am,
again?
you have written that in order the Lagrangian to be Lorentz invariant, the V of phi should be trivially invariant. But it is usually seen that while constructing models under particular symmetry, we check for the potential minimization part under the symmetries that has been considered. So how is this different from this concept V of phi is trivially invariant?
So when I said, go ahead, sorry.
Yes, please continue.
So when I said that it's trivially invariant, simply this is a consequence of the way that scalar fields transform under Lorentz. So I mentioned that a scalar field transforms in this way. So it doesn't transform under Lorentz. And that's why if you write down a scalar potential of this type, then also that potential doesn't transform, so it's invariant.
Okay.
But this is if you want, a consequence of the fact that I'm taking a real scalar field with those property of transformations under Lorentz, and then I see what happens to the potential. This is not, you know, this is a consequence of having a scalar field.
Okay. Okay, thank you.
Okay, sure. So this is for scalar fields, and then for fermion fields.
There's another question.
Oh, sure. Sorry.
By Engame again.
Yeah, hi, sorry. I was just thinking about what you said about global and local symmetries, and I was wondering, do we consider Lorentz symmetry a global symmetry?
Yeah, so we don't, yes. So that's right. I didn't, so I'm putting it on a different footing. So the global symmetries, let's go back. So the global symmetries I was mentioning here, global symmetries that are accidental. So that come out once that I impose, you know, my Lorentz symmetry, my gauge symmetries, and so on. So I was putting them in a different footing, but definitely, so the Lorentz symmetry that we are considering is not gauged. So this is also a symmetry of that type. Even though I was putting that on a different footing.
But would that change if the metric, well, if you're not talking about the Minkowski metric and change the metric? Yeah,
so it's a bit different than, So when I speak about gauge symmetries, the idea is that, or local symmetries, so the gauge symmetries I was putting here for the standard model, these are local in the sense that the transformation will depend on the specific point in space-time. Yeah, so this is sort of different than what you are thinking about having a non-Minkowskian metric. I don't know.
Yeah, sorry, I just asked that because I usually deal with, I guess, like cosmology and particle physics a lot, and I was just wondering, like, in the case of like having a non-Minkowskian metric, then I guess like the Lorentz symmetry in that case is not really like a global symmetry. It'll depend on space-time coordinates.
That's right, but it's a bit different because you don't. I mean, you don't have the same way of treating it, right? As you know, introducing, as we see, gauge bosons that are connected to these local gauge symmetries and so on. But yeah, I agree that here what you can do is, instead of using this Minkowski metric, you can use you can take a metric that does depend on your space-time, on your x. Yeah.
Right. Thank you.
Okay, very good. So then, of course, I mean, just to connect to what we have seen at the very beginning of this class, you can use this Lagrangian to write down your equation of motion, and the equation of motion that you get is your Klein-Gordon equation. So what you get is that the box operator applied to the phi field is equal to minus the derivative of your potential. Okay, just to, as I said, connect to what we have seen at the very beginning of this class. So this is all I wanted to say about scalar fields, and then the second example that I want to mention is the Lagrangian for a fermion field. So what I take here is a psi field that is a, in this case, a 4-component Dirac spinor. And so this field will describe the spin 1/2 particle when it is quantized. And then again, the Lagrangian that I might try to use is a Lagrangian of this type. So here, so let me write it down and then I will discuss. Minus m psi, where this psi bar is defined as psi dagger gamma 0. So these are the gamma matrices that do have this anti-commutation properties, namely plus gamma nu gamma mu is equal to 2 times the metric. So this is our Clifford algebra. What one can do in, I won't discuss this because it would take me quite a bit of time, but what one can check is that indeed this Lagrangian that I brought above, this LF, is again Lorenz invariant. So I find Maggiore a nice book explaining and showing in details this aspect. So for the people interested, I would suggest you to take a look at the book of QFT by Maggiore. So this is one of the references that I showed you at the very beginning. And then again, so this is the first thing that we can check. And then the second thing is that using the equation of motion and using this Clifford algebra, telling us how the gamma matrix is anticommute, we can show that we obtain the Dirac equation. So namely that I gamma mu, the derivative, minus m applied to psi is equal to 0. Okay. And we see that indeed this type of Lagrangian is the Lagrangian that is at least part of the Lagrangian that is describing the quarks and leptons of the Standard Model. Now, since we're speaking about fermions, let me take this as an opportunity to define two quantities that we'll use quite a bit tomorrow when we'll discuss the weak interactions. Namely, we can define the helicity of a particle. So let's maybe open a small parenthesis. So what is the helicity of a particle? So this is defined as the product between the spin and the momentum. So S is the spin, and P is the momentum. So these are three-dimensional vectors, and then we are used to normalize this with the absolute value of the momentum. It's easy to demonstrate that this quantity is actually not Lorentz invariant. So if you choose a different Lorentz frame, you will get a different answer. We can use the helicity to define right-handed and left-handed particles. So we'll have a right-handed particle that is a particle that has a spin that is in the same direction as the momentum. And then we'll have left-handed particles where the spin is instead in the opposite direction. So we can use this property of particles to do actually our calculations. But there is another property of particles that is connected to helicity that is Lorentz invariant. That is what we call the chirality of a particle. So what is the chirality? So the chirality for a four-dimensional spinor is defined by the gamma 5 operator. So what we have is that if we take a massless spinor, what we can show is that actually the chirality and the helicity are describing the same property. So chirality is the same thing as helicity. Again, we should not forget that this is only in the limit, in the massless limit, in the sense that we have the energy of the particle that is much bigger than the mass. And so in this limit, what we can demonstrate is that if we take the gamma 5 matrix and we apply to a right-handed particle, then we get the same. Sorry. And instead, if we apply it to a left-handed particle, we get a minus sign. Okay. So this is a spinor for a particle. So a 4-dimensional spinor. And then for completeness, we can also ask what happens if I apply this operator to an antiparticle, and then we have sort of the opposite behavior, in the sense that if we take the spinor V for a anti-particle, we have that this is equal to minus V, and then similarly, we have this with a plus. Okay. I see a question in there.
Yes.
Hello, Stephanie.
Hi.
Yeah, I have a couple of questions from Helicity. In the context of Fermion, to distinguish between left-handed and right-handed, we need this Helicity quantity. But my question is from photon, that in a photon we have also defined polarization, and because it is massless, we already know that there are two polarization state we call the left-handed and right-handed polarization states of photon. So how it is different from polarization, and if it is not different between I mean helicity and polarization, why we called it in a different name, helicity here?
Yeah, I mean the physics that that is described is similar, if you want. Typically, people use this notion of I mean the word of helicity to describe fermions. But if you want, I mean, this is just to understand what is the direction of the spin with respect to momentum and what is. But I mean, in terms of physics, there is not much more to it, right? Yeah.
Okay.
Obviously, yeah. Go ahead.
Yeah. So because we are talking about fermions, so we are using new kind of word instead of polarization. That is helicity.
Sorry, say it again.
In case of photon, we are talking about polarization. There also photon can move, and it may have a component along spin or to the opposite of spin. So
Sure.
there it is polarization, but here it is helicity, and you are talking about, because we are talking about fermions, so we are using this new word, helicity.
Yeah, but I mean, you can obviously you can apply this the same definition also to a photon or to anything that has a spin, right?
Okay.
And then you can compute your helicity also for photons. It's just a matter of what is the the observable that is most convenient to describe a specific system. But
Okay.
no one is telling you that you cannot compute this quantity here also for particles that are not fermions. Yeah, this is what I wanted to say.
Okay. And another question, I am not too much aware about the chirality, means other than these matrices and other these things. So why we need this chirality or chiral quantum number other than helicity? How helicity and chirality is different?
Yeah, so the way I presented this here, I mentioned that in the massless limit, they are the same thing. But this is only in the massless limit. So if you take a particle that has an energy that is comparable to the mass, this is not anymore the case. So this is the first thing that one should keep in mind. The second thing that is very important to have in mind, and this relates to the lecture of tomorrow, is that the chirality is a property that is very important when we study the weak interactions. Namely, that we'll see that only, so let me write here for tomorrow. So what we will discuss is that only chirally left-handed fermion fields couple to the W bosons of the weak interactions. So when we study weak interactions, we'll see that only a specific class of fermions do couple to the weak interactions. So in this sense, it's very important to use this idea of chirality to describe and to identify different type of fermions. Okay.
Okay.
And this, yeah, we'll develop this much more tomorrow. But that's why I'm introducing that here, because this is a property that is differentiating particles, those communicating to the double boson, those that are not. Okay.
There is
other questions?
one question by, I think, Engame.
Sorry, I'm not sure if the scope allows us to talk about this stuff, but I guess I was wondering, okay, so when we write down representations of the Lorenz or the Poincaré group, and then we have SU2L cross SU2R, I thought that the left-handedness or right-handedness corresponds to whether the representation of the set fermion is like 1, 0 or 0, 1.
Yes.
And okay, so then I guess like I always get like, this confuses me. Then I guess like if you want to talk about chirality or the handedness of a particle in terms of the representations of the Poincaré group, like how would that like correspond?
Yeah, so basically, yeah, so this is obviously a long discussion, but so this is when maybe let me think if I can say a couple of things.
I'm also happy to wait and we can discuss this later if you think this is outside of the scope.
Yeah, I would be happy to discuss it later, but maybe a couple of words is, so when I mentioned here that we have this fermion Lagrangian and we can show that it's a Lorenz invariant, and I point you to the Maggiore book. This is exactly this type of discussion. So basically the idea is that you split your Dirac spinor in two parts. You have your left and right part. And this is so these are while spinors that they do transform in a different manner, as you say, under the Lorenz transformations. And this, yeah, using this, basically, you can demonstrate that this is the Lagrangian is Lorenz invariant, and this is connected precisely to what you are asking. But yeah, it's quite a bit of a long discussion that I was not planning to, go through in details.
I'll just wait till after then. Thanks.
Sure.
Next is Giovanni Della Valle.
Hi. My question was just, as we said, that we can define chirality for all the other vector fields or any other particle. Just here we have the gamma 5. How would just an idea of definition of chirality for, I don't know, for W